Have you ever stood in an airport and noticed one simple but odd thing? On some airplanes, the engine at the tail, mounted to the fuselage. Why is that? A design accident, a fashion among engineers, or strict engineering logic? Today we'll look in detail at why engines are placed where they are, and how the behavior of a liner with an underwing layout differs from an airplane with tail-mounted engines. There will be many important details, from maintenance convenience and economy to aircraft behavior in an engine failure and stall characteristics. Make yourselves comfortable. Let's begin. The first and perhaps most obvious argument in favor of the underwing scheme is maintenance. When an engine hangs under the wing, it is accessible to mechanics without lifts and complex rigging. You roll a trolley up, change the oil, perform diagnostics, and checks. Less time on the ground means lower operational costs for the airline, and in counts. This is an important, practical reason for wing engines. The second, no less important factor is the size of modern engines. Turbofan engines grow larger with each generation. Fan diameters increase, bypass ratios rise, and efficiency and thrust go up. To suspend such massive units, you need a strong support. Under the wing sits one of the stiffest and most heavily stressed structures of the airplane, the wing box with spars and ribs. It is precisely designed to carry loads, fuel weight, lift, bending moments, and, of course, the mass of the engines. Trying to hang the same engine on the tail would require radical reinforcement of the fuselage, leading to greater weight and worse balance, economically and structurally unprofitable. Another practical limitation is landing gear height. Sometimes that dictates compromises. Take the Boeing. So designers had to get creative, making the engine. This solution is a compromise between aerodynamics, ease of maintenance, and engine dimensional requirements. If a manufacturer needs a large four-engine liner, like the A340 or Boeing 747, placing four engines under the wing is much easier and cheaper. Theoretically, you could arrange them differently, but practical and economic considerations make the underwing scheme the natural choice for such aircraft. Let's talk about wing loads. The wing is not a flat panel. Inside, it is the wing box that carries bending moments. In flight, lift tries to bend the wing upwards, and the heavy engines under the wing act as a counterweight. They pull the wing down and thus reduce the bending moment. This lowers fatigue loads on the structure and extends the wing's service life. Simply put, an engine not only weighs and pulls, it can't ignore flutter either, an aerodynamic vibration. Placing a heavy engine under the wing shifts the wing center of mass and changes its natural frequencies, which in some cases makes the system less prone to resonant phenomena. This is one of the rare examples where added weight is beneficial for dynamic stability. Passenger safety is another argument. In case of an engine fire or disintegration, the underwing layout places the unit farther from the pressure cabin. Fire, debris, and high temperatures stay further from passengers, so the risk of combustion products entering the cabin is lower than with tail-mounted engines, where the engines are closer to the fuselage. Noise. The main noisy components of an engine are not only the fan but also the jet exhaust, and the underwing scheme partially screens that sound. The wing casts and disperses some acoustic waves, so passengers under the wing. However, the main ones is behavior during engine failure. An engine suspended far from the longitudinal axis creates a large lateral moment arm. If one engine suddenly stops producing thrust, the other continues and pulls the airplane sideways, creating a yawing moment. The farther the engine from the axis, the stronger the effect. To compensate, aircraft with underwing engines have large vertical tails and powerful rudders. That is why types like the Boeing 737 or Airbus A320 have rudders that are noticeably larger than those of most aircraft with tail-mounted engines, where the lateral moment arm is smaller. Another interesting feature is thrust-pitch coupling. On aircraft with underwing engines, changes in thrust produce a moment about the center of gravity. Add power, the airplane tends to raise the nose slightly. Reduce power, the nose drops a little. The pilot has to coordinate power and the control column together, especially on approach. Reduce thrust, you pull it back. On modern variants, Max or Airbus A320neo, this effect is stronger simply because the engines are bigger and create a more powerful moment. If engines are mounted at the tail, the engineering logic and the behavioral picture change. The tail configuration gives a substantial advantage in cabin quietness. The jet plume and nozzle noise are located behind the passenger rows, especially if you are seated in the front or middle of the cabin. In addition, tail engines are usually higher off the ground, reducing the risk of FOD ingestion, foreign objects from the runway like stones, chunks of ice, gravel, and debris. For business jets and regional aircraft that often operate from small fields with imperfect surfaces, this is a very important plus. The tail scheme opens another practical possibility. On some liners with rear-mounted engines, for example, the pilots can sometimes use reverse thrust to gently back away without a tug. Because the reverse thrust jet is directed back and down, the chance of sucking up debris from the surface is minimal. On aircraft with low-hung engines, like the Boeing 737, reverse thrust can lift particles from the surface that may be ingested into the engine and damage the compressor, so that maneuver is inapplicable and even dangerous there. But the tail layout brings its own structural challenges. Engine mass shifts aft. That requires careful center of gravity calculation. Designers often lengthen the nose to move the center of gravity closer to the wing. That is why the MD-80 and Boeing 717 show a relatively long nose and a compact rear fuselage. Fuel, as in most airplanes, is stored in the wings, so long fuel lines must run to tail engines. That increases system complexity. In a pump failure, gravity feed works worse, and additional. Another serious aerodynamic